Alrighty, last podcast for chapter 4. Okay, so molarity. We know what molarity is, right? Okay, you can have the same compound in there, but the solutions can be very different because you may have more of the solute, higher concentration, more dilute. It can be very different. Okay, we use molarity as one way to measure the concentration of solution. You should also remember molality. Sometimes density. There's other ways as well. So molarity, as we know, is moles of solute per volume of solution in liters. Okay, just take a minute and think about the molarity though. So say I have a solution and I have 1 molar. So I have 1 mole of solute per liter of solution. Okay. What happens if I leave that beaker of solution out overnight, say time has gone on, and some of the water has evaporated? What has happened to my solution? Think about it. Okay, so the water evaporated out, I got less water, so there's less solution. Did anything happen to the solute particles? The answer is no. They stayed there. Typically the solute has a much higher boiling point or much lower vapor pressure, depending on how you want to look at it. So the water leaves, typically the solute remains behind. So in this solution here, more concentrated, less concentrated. Hopefully you're thinking more concentrated. So the concentration is going to be something greater than 1 molar. Mixing a solution. We know, hopefully, from our first lab that the equipment we would want to use if we do want to have a fairly precise or accurate solution, we're going to use an electronic balance. Probably the more decimal points the better, and we're going to use a volumetric flask. Weigh out or mass out a known amount of the solute, add the solute to the volumetric flask, and then the solvent is added to the line that is on the neck of the flask. I found a link, it's kind of funny, to show how you do this. I don't want my ink. Here it is. It's a YouTube video. Just watch. The music is wonderful.
Está parado el fraile de la Merced. Ay, el fraile de la Merced. Con los hábitos alzados, enseñando el chuchumbe. Con los hábitos alzados, enseñando el chuchumbe. Que te vaya bien, que te vaya mal. El chuchumbe te ha de tomar. Que te vaya bien, que te vaya mal. El chuchumbe te ha de tomar. Vaya. De la Merced. Ay, del barrio de la Merced. Y cómo se zarateaba metiéndole el chuchumbe. Ay, cómo se zarateaba metiéndole el chuchumbe. Que te vaya bien, que te vaya mal. El chuchumbe te ha de tocar. Te vaya bien, te vaya mal. El chuchumbe te ha de tocar. Por aquí pasó la muerte con su aguja y su dedal. Por aquí pasó la muerte con su aguja y su dedal. Buscando casa por casa, un hoyo que reventar.
I don't know about the music. I'm sorry. I just thought that was funny. The only thing that I would do different is I would fill up the volumetric flask just about halfway to 3/4 and really not go into the neck yet, and swirl it so that everything dissolves. Then fill it up to the line, then invert it. We'll also make solutions where we just use a stir bar, and those are just fun. Okay. So, dilution. Sometimes we make solutions from solids. Okay, sometimes we make them from a more concentrated solution. Okay, and calculations we'll get to in a minute. Just using a pipette, you deliver a volume of the solution to a new volumetric flask, and then you add the solvent to the line on the neck of the flask. And if you look at hopefully a quick video on that.
Suppose we wish to form a solution of known concentration by diluting a more concentrated solution of known concentration. We wish to prepare 250 milliliters of a 0.100 molar copper sulfate solution, beginning with a 1 molar stock solution. We first withdraw precisely 25 milliliters of the stock solution with a 25 milliliter pipette. This amount of stock solution is then added to the 250 milliliter volumetric flask. We then add water and swirl the flask to ensure good mixing with the added water. More water is added to bring the volume to the mark on the flask that indicates precisely 250 milliliters. We now have our final solution of 0.100 molar copper sulfate.
Okay. So, what math were they using? This is one that you've seen, probably. I caution you to be very careful using this particular equation. You will very seldom see me use this particular equation. And I'm going to ask you, why does this equation work? Why does it work? Why does m of the more concentrated solution times the volume of the more concentrated solution equal the molarity of the dilute solution times the volume of the dilute solution? Why does that work? Well, think about it. What is molarity times volume? What is molarity times volume? Well, that's just moles. Okay. So moles is equal to moles. So it goes back to that evaporation example. What are we not changing? We're not changing the number of moles. We're making a solution more dilute by adding more solvent. Okay. Theoretically, I guess you could do it the other way, but you're not going to boil water off really. You're really going to start from more concentrated and make more dilute. Typically, how I would calculate it is I would start with the well, actually, you know what? I'll do a problem like that in class. You ask me to do a problem like that. Say, hey, show me your way of doing a dilution problem, and I'll show it to you. How exciting is that? All right, this is just a chart. I included it. If it helps you, great. If not, just skip over it. Okay. Titration. We're going to be looking at titrations quite a lot this year. The important points to point out here is one, the solution that you want to know the concentration of, typically in acid or a base, most often in acid, but not always. You're going to pipette a certain amount into an Erlenmeyer flask. Sometimes we use beakers just because we're using the pH probes and it's too much to fit into the neck of an Erlenmeyer flask. You're going to fill a burette with a known concentration of either a base or an acid, and then you're going to use the stopcock and deliver that acid or base into the Erlenmeyer flask. If we use a pH probe, we don't always use the indicator. Most often, if you're doing just to find out what the concentration is, you use an indicator and you go just till it turns pink. important thing to note is the initial volume reading and the final volume reading. You know the molarity of this concentration, so the molarity of the sodium hydroxide times the volume used, which is the final minus the initial, is going to give you the moles of sodium hydroxide that was used to get what they call the end point. Once you know the moles of base needed, you can relate that to the moles of acid. It depends if you have a monoprotic or a diprotic acid. Monoprotic 1H, diprotic 2. I'll let you figure out what triprotic means. So then it's just a more or less a stoichiometry problem. One last little video. Get full screen for you.
Quantitative addition of a solution of known concentration to one of unknown concentration, resulting in a chemical reaction, is called titration. Acid-base titrations are among the most common when a standard sodium hydroxide solution is added to a hydrochloric acid solution. The neutralization reaction occurs. A pH meter is employed to measure the acidity of the solution. To illustrate, let's add 0.100 molar base to precisely 50 milliliters of a 0.100 molar acid solution. The pH increases slowly at first. As the amount of base added approaches that required for complete neutralization, that is the stoichiometrically equivalent amount, the pH begins to increase more rapidly. The last few drops of added base change the pH from about 3 to 7. The pH is 7 when precisely 50 milliliters of base have been added. We are then at the equivalence point, or end point, at which the stoichiometric amount of base required to neutralize the acid has been added. Addition of 1 drop of NaOH beyond that needed to neutralize the acid causes the pH to increase from 7 to about 10. Thus, the end point of the titration can be determined with high precision.
Okay. That ends Chapter 4. Looking forward to seeing you in class. Thanks.